can see a metallic bond formed by marbles. A metallic bond is the force of attraction between balanced electrons and metal atoms. A metallic bond is a type of chemical bond formed between positively charged atoms in which the free electrons are shared among a grid of cations, negatively charged. The electrons act as a glue, giving the bond a structure, and the metal atoms acting as a nuclei for the electrons. So let's say you take water and put it in a container and allow it to start evaporating. The space above the surface of the water will start getting water molecules. It's a gas now. And if you put a lid on top of it, all the particles are trapped as the water starts going back into the water, into the water vapor. Now you reach the point in which the existing evaporation rate is the same as the entering condensation rate, and you reach equilibrium. So when those two rates equal, you establish a constant pressure into your container, and the pressure is called the vapor pressure. So in scientific terms, that is called dynamic equilibrium, meaning when you look at it, you can't tell anything's happening, but actually there are billions and billions of molecules leaving the surface of the water and also re-entering it, so there's no net change, but you have established vapor pressure. A pair that is not shoved between two atoms, it's just an electron pair sitting on one atom. Once a central element starts to get lone pairs, it's going to compress the bond angle, it's going to make it smaller. Lone pairs want to be as far away as everyone else. It's up here. And this causes them to get smaller, and that actually makes the bond angle smaller. The ideal bond angle would be 109.5. This one would be 107. So there's a lone pair, wants to be away from everyone else.
As you see here, melting and boiling are two different things. With melting, each substance has its own different melting temperature, but ice will start to melt pretty easily and melts down into water. And as you see here, it went from ice to boiling in roughly like 4 minutes. So you get to see how boiling, which is from a liquid to a gas, is vastly different from, and there's the gas heading up, is vastly different from melting, which is from a solid to a liquid. Ions are also very easy to understand. If we look at this carbon, which is a -1 carbon, which just means it has an extra valence electron, it's equal to nitrogen on the table and 3 away from neon, which is where it wants to be. So if you would give it 3 more, just imagine those all landed correctly, it would become a -4 carbon, making it equal to neon and where it wanted to be. When it comes to atomic radius, it's pretty easy to understand. First off, just as examples, imagine these to be the radiuses of the elements. So francium is located down here, and then sulfur is up here. And as we see from this, as it goes from right to left and the top part of the table down to the bottom part, it increases. So you can see from this example that francium is a lot larger than sulfur, and that carries over when you look at sulfur and francium on the table.
My name is Marino, and today for my chemistry project, I'm going to be doing the 3 different types of covalent bonds. Before we get into everything, a covalent bond is a type of bond that just does sharing. It doesn't give up anything, it just shares. So let's get into the 3 types of bonds. So this is the model. I have the first bond we're going to be getting into is the single bond, otherwise known as a hydrogen bond. The reason why it's called a hydrogen bond is because the fact that it's a single bond, it shares 2 electrons, as you can see right there. Now, the way you would write it is you would have an H standing for 1, and then you would have a single line connecting another one. Now, this line right here accounts for 2 electrons. So because if we look back here, this first orbital can only hold 2 electrons at most. So when you have the sharing going on, these 2 electrons revolve around both, meaning that they are both sharing going on, these 2 electrons revolve around both, meaning that they are both satisfied. Now, if we move on to the next example right here, the double bond, otherwise known as a oxygen bond, each each oxygen atom six has 6 valence electrons, meaning that it still wants 2 more. That way it could be all balanced. So as you could see here, you have these 2 theoretically belonging to only this one, and these 2 theoretically also only belonging to this one. However, when you share them, they both revolve around the same, meaning that they both have 8 on its valence electron orbital. Now, if you wanted to write it down again, you would have an O, and as you said here, each line accounts for 2 electrons. So because oxygen needs 2, we're going to do one line and another one. Because there's an electron here, and one here, one here, and one here, and they're both being shared back. Now, for nitrogen, it has 5 valence electrons. For it to be completely balanced, it just needs 3 more. Now, just as we said here, these 3, 1, 2, 3, theoretically only belong to this atom, and these 3, as you can see, belong to this side over here. Now, for them to both be balanced, they obviously have to be shared. Now, because it's a covalent bond and they're both sharing, these 6 will constantly be shared to the valence electron orbital of both of the atoms, meaning that they are both going to be balanced. Now, just as we did for the other 2, if we write it out, we're going to have N standing for nitrogen, and we're going to have 3 dash marks because they both account for 2. There's going to be 1, 2, 3, 1, 2, 3, and let's not forget to put that. So basically what is happening here is the same thing that I showed you with the model. These 3 will be shared with this one as well as stay belonging to this one and vice versa. Thank you for listening, and thank you.